In the previous lecture we have begun a discussion of the energy band diagram, which is a very important tool in the analysis of semiconductor devices. We have mentioned two types of energy band diagrams which are complementary to each other. One is the EX diagram, which tells you the allowed energy levels of electrons as a function of distance within a device. Now this diagram, the EX diagram, helps you to analyze the distributions of electron concentrations, hole concentrations, electron current density, hole current density, electric field and potential within a device. On the other hand, the EK diagram, where you represent the allowed energies as a function of the wave vector which reflects the crystal momentum of the electron. The EK diagram helps you to estimate the effective mass, the group velocity of the electron and the crystal momentum, and this EK diagram is useful to analyze the interaction of an electron or a hole with other carriers, impurities, phonons and photons. We gave a qualitative model of the energy band diagram in which there were two approaches. One approach, that is the Bloch approach, develops the allowed bands of energies in a crystal for electrons from the single energy levels of electron in an isolated atom. On the other hand, the Brillouin approach develops the forbidden energy bands for electrons in a crystal from a continuous band of energies associated with a free electron. Then we began a discussion of the quantitative model of the energy band diagram. First we took up the EK diagram. Now for the EK diagram we considered the rectangular potential well, and this EK diagram is what we are going to develop further in this lecture. Now here is the rectangular potential parabola. The allowed energy levels shown here, where so the boundary conditions psi equal to 0, the wave function at x is equal to 0, that is at the left end of the well, and the wave function at the right end of the well here were both approximately 0 because the height of the potential barrier was really large, and because of the boundary conditions you get, and this discretization leads you to discretization of the energy. As a limiting case of L tending to infinity, you get the picture for free electrons, which is a parabola for E as a function of k, in which all energies are allowed. In today's lecture we want to develop the EK diagram for an electron in a periodic crystal potential, starting with the solution of the Schrodinger's equation. Now let us look at the features of the EK relation for electrons in a periodic potential one by one. This is the approximate form of periodic potential. The first feature of the EK diagram of electron in a crystal is that E is a periodic function of k with periodicity 2 pi by a. You can see this here. So EK relation is a periodically varying function and the period is 2 pi by a. So you can see from here that this end to this end here is one period, or from 0 to 2 pi by a is one period. Okay. Now how do we explain this feature? We will see that. First let us list all the features. The second feature is that the Schrodinger's equation has no solution for certain energy bands when k is real. Now these bands are shown here in grey color. Okay. So they are the forbidden energy bands. So for these energies the Schrodinger's equation has no solution. finally, E is a multi-valued function of k. So, you see for any value of k you have several values of energy, multiple values of energy. Okay? So, these are the three features which we need to explain on the basis of Schrodinger's equation solved for a periodic crystal potential. Let us look at the first feature. E is a periodic function of k with periodicity 2 pi by a. Now, this is the Schrodinger's equation for electrons in a crystal. UCx is the periodic potential. The property of UCx is that it is periodic with period a, which is the distance between the atoms. So, UC of x is equal to UC of x plus a. Now, there is a theorem called Bloch's theorem which says that if the potential is periodic as considered here, then the wave function which is a solution of the Schrodinger's equation is of this form. U of x, here the suffix k indicates that this u contains k as a parameter. So, u of x into e power j k x. Now, for a free electron you recall that the solution was just e power j k x. Okay? So, here what is happening is the periodic potential is multiplying this e power j k x with an envelope function which also is periodic with a period a, like the crystal potential. Now, this is the important result that we simply import from the Bloch's theorem. Now, based on this important result for the wave function psi of x, how do we show that E is a periodic function of k with periodicity 2 pi by a? Now, while we do that, let us first look at some graphs of the wave function psi x, the envelope function or the Bloch function ux with a suffix k, and e power j k x and so on. Now, here is an example. These calculations are done numerically and I have picked them up from a figure available in Lundström's book. So, if UCx is periodic having a shape as shown here, then u of x has a shape something like this. The points here indicate the location of the atoms in the crystal. E power j k x on the other hand is like a sinusoidally varying function. You can take either the real part or the imaginary part. Now, when you multiply these two, u of x and e power j k x, you get the wave function. Now, you see that the wave function is fairly complex. Okay? This wave function is obtained by multiplying this function and this function. So, this gives you some idea of the various functions that are there in the solution of the Schrodinger's equation for periodic potential. Now, let us move on to show how E is a periodic function of k. Now, the first point to note is that the E k relation is even, that is E of k is equal to E of minus k. Now, this is straightforward because if an electron is moving in the positive x direction or moving in the negative x direction, that is from right to left, it sees the same form of crystal potential, and therefore the energies associated with these two movements should be the same. That is essentially what is said by this particular relation. Okay? So, the k vector here indicates movement in the positive x direction, whereas minus k indicates movement in the negative x direction. Now, we will establish that E of k is equal to E of k plus 2 pi by a based on this particular wave function solution given by the Bloch theorem. So psi of x is equal to uk of x into e power jkx. Now, since uk of x is periodic with a period a, let us multiply this right hand side and divide by a function e power j into 2 pi by a into x. So, I am going to multiply by e power minus j 2 pi by ax and e power j 2 pi by ax. Note that product of these two is 1. Now, since x is periodic with a period a and this function also is periodic with a function with periodicity a, you can see that here when you put x is equal to a, it becomes 2 pi. When you put x is equal to 2a, it becomes 4 pi. So, you know that for integral multiples of 2 pi, this quantity will be the same, it will be unity. Therefore, I can club these two and write this as another periodic function, okay, which has a periodicity a multiplied by this part appears as e power j x into k plus 2 pi by a. Now, this new form of the function is also psi of x. This means that the energy that is represented by this function and the energy that is represented by this wave function, both the energies must be same, and therefore we can write the energy which is a function of k should be the same if the k is replaced by k plus 2 pi by a. Okay? So, this part is energy associated with this function, here you have k, and this part is energy associated with this function and where you have k plus 2 pi by a here. Okay? So, this is how we derive the condition that E is a periodic function of k with periodicity 2 pi by a. Next, the Schrodinger equation has no solution for certain energy bands when k is real. Now, let us see how we show this. Now, this is our periodic potential approximate form. The points here indicate the location of atoms. The potential well here is having a length b, okay. The origin is set up here at the left end. The height of this potential barrier is u naught and the thickness of the barrier on the left hand side here is c. The distance between the two atoms, which is a, is nothing but b plus c. So, this is the lattice constant. Now, this is your Schrodinger's equation and this is your solution based on the Bloch theorem. Let us consider the interval 0 to b, x 0 to b, that is this interval here. In this interval, the potential is 0, okay. The UCX is 0, that is what is shown here. The envelope function or the Bloch function ux, let us indicate that as u1x. The suffix k indicates that this ux also contains k as a parameter. So, this is the u1 function in this region. the equation for u1 would be obtained by substituting this function, writing here u1 instead of u of x, right here u1x. Okay, substitute this here, and this differential equation reduces to this particular differential equation, where we have used alpha to indicate this term, which is square root of 2 m naught energy by h cross square. So this term you obtain from this part of this equation. So in a simplified form, when you write, this is the way the equation will turn up. This differential equation has the solution of this form: a into e power j into alpha minus kx plus b into e power minus j into alpha plus kx, because this is second order differential equation. Now this solution can be easily seen by substitution. You are getting alpha minus k because you have alpha square minus k square here as the coefficient. Okay, so you get alpha minus k as well as alpha plus k, the two things. If you do a similar solution for x lying between 0 and minus c, that is this region, now here your uc of x is equal to u naught. So this u naught is the value of the crystal potential in this region. The Bloch function is u2x. Now we define a parameter beta, which is different from alpha in this term that here instead of energy for alpha you have energy minus u naught, which is the potential here. Now in terms of this beta, if you write the differential equation for u2 of x obtained by substituting this function into this Schrodinger's equation, then this is your differential equation and this is your solution. This is similar to the solution u1 x with alpha replaced by beta. So this is the summary of the solution for u1 of x and u2 of x, valid for the two ranges x between 0 and b and x between minus c and 0. Now the coefficients a, b, c and d are to be determined by using the following boundary conditions. Now look at these boundary conditions. The boundary condition u2 at x is equal to 0 should be equal to u1 at x is equal to 0, because the wave function should be continuous across the boundary here. That is the statement which is being made by this equation. Similarly, the derivative of the wave function should also be continuous here. Now that is what is reflected by this equation. So d by dx of u2 at x is equal to 0 is equal to d by dx of u1 at x is equal to 0. Now exactly similar conditions should apply at the other end, either here or here. Now because the function is periodic, we can say that the value of the wave function at this end should be equal to the value of the wave function at this end, right. This is the same as saying the value of the wave function when you approach this point from right should be the same as the value of the wave function you approach the same point from left. Okay, so this region is identical to, so this region is identical to this region and this region is identical to this region. So that is why this condition is formulated: u2 at minus c, that is here, is equal to u1 at x is equal to b. So u1 at x is equal to b at this end. So value at this end here should be the same as value at this end. Similarly for the derivatives, okay, the derivatives should also be same at these 2 points. So we substitute these boundary conditions in this equation to get a, b, c and d. Now when you do that, you will find that non-zero A, B, C, D is possible only if this particular condition is satisfied. Okay? So this equation is obtained as follows. So you apply the boundary conditions that we have just talked about and write equations for A, B, C and D. Now in these 4 equations, if you want non-zero A, B, C, D, the only way it can be done is by getting this particular relation. So let me explain that. So the equations will turn out to be of this form: something into A plus something into B plus something into C plus something into D is equal to 0. Now all the 4 equations will be of the same form with different coefficients coming here. So you have 4 such equations. Okay? So you have 4 such equations. Now evidently A equal to 0, B equal to 0, C equal to 0, D equal to 0 is a solution, but that is a trivial solution. So that solution won't work for you. Okay? So the only other solution that you can get, how do you find that? Well, you express A in terms of B, C and D and substitute here, then you express B in terms of C and D, substitute in the next equation, then you express C in terms of D, and that is how you can convert this entire equation to an equation of the form something into A equal to 0 or something into B equal to 0. So all these 4 equations can be converted into this form, right? Something into C equal to 0 or same thing D equal to 0. So if you don't want the solution A equal to 0, the only other non-zero solution for A is possible if you set this term in the bracket to 0. Now this is the term that we are talking about here. Okay? So when you set that term to 0, you get this equation. Okay? So the coefficient of A, or you can take coefficient of B, right? You can take coefficient of any of these. Now this is the key result based on which we can show the existence of forbidden bands. Let us see how. Now first point to note is that for E less than U0, so U0 is the height, for energy less than U0, beta is imaginary. You can see here, if E is less than U0, this is negative and therefore beta is imaginary. But the right hand side of the above equation is real. So here, even if beta is imaginary, this will be real. This is an important point to note. Now how do you get this? Because beta square is real even though beta is imaginary. Now here, this beta you can write it as some j times some constant. Now sine of j times some constant is nothing but j times sine hyperbolic of the same constant. Sine of j into some gamma, let us say, is equal to j into sine hyperbolic gamma. You can show this very easily, right, using exponentials. So what will happen is that a similar condition can be shown for cos of imaginary constant here. So well, we actually do not need that part, we need only this part here. So here you will get a j out of the sine, and this beta will also contain a j, and this j and the j coming out here when you write this in terms of sine hyperbolic function of a real quantity. So that j will cancel, and that is how this part will be real. Okay? In fact, this part is real even when this j is imaginary. Now let us look at this function on a plot. So the right hand side of the function, that is this part, has been plotted as a function of energy, because alpha and beta here, alpha beta, these are functions of energy which we have defined in the previous slide. So therefore this whole thing is a function of energy. So when you plot, you get a periodic function of energy. The right hand side is a periodic function of energy, evidently because sine, cosine and so on, these are all periodic functions. Now what is important here to note is that the amplitude of this variation goes beyond 1, okay. So it goes below -1 and above +1. Now this is the important result that tells you why certain energies are not possible, okay, for electrons in a crystal, because if the right hand side here goes either less than -1 or more than 1, then that is not allowed, because the cos function has a maximum value of 1. If I take the magnitude of this function, it cannot exceed 1. Therefore for those values of E for which the magnitude of this function exceeds 1, that is indicated by this boundary, okay, -1 and +1 here. So when this function goes beyond, crosses these boundaries, in that region the solution of the Schrodinger equation does not exist, okay, because k is no more real for these regions. So these regions are therefore shaded to show the forbidden bands. So these band of energies here, similarly this, where the right hand side is going, the magnitude of the right hand side is going beyond 1, these energies are not allowed, because for these energies the k is not real. So the E values for which the modulus of right hand side is more than 1 are forbidden as k becomes complex. Now these are the bands that are shown on the Ek diagram here, okay. So each of these bands shown here actually correspond to these bands which arise from this particular equation. Now let us look at the final feature of the Ek diagram. This is that E is a multi-valued function of k. How do you get this? Well, that is also obtained very easily from this graph, which clearly shows that for a given k or a given right hand side, for a given k or a given value of the right hand side, there are multiple values of E. You can see that here, for any given k there are many values of E. That is again because of the periodic nature of the right hand side, okay, and that is why here E is a multi-valued function of k. So for any k you have multiple values of E. So that is how one can show the three important features of the Ek diagram of an electron in a periodic potential. Now here is an assignment for you. Simplify the equation cosine of b plus c into k equal to minus of alpha square plus beta square by 2 alpha beta into sine of alpha b into sine of beta c plus cos of alpha b into cos of beta c, where alpha and beta are given by these quantities for the following conditions. A, the energy of the electron is much greater than u naught, which is the height of the rectangular potential distribution, okay, and therefore from your results show that the forbidden band becomes progressively thin as energy becomes more and more, as energy becomes higher and higher. Part B, assume u naught into c is a constant. So u naught into c, let me draw that potential distribution for you here. Now this distance is c and this height is u naught, okay. and this distance is b. So this is your rectangular potential. This is x and this is uc of x. So we are saying assume u0 into c, that is the area under this, as a constant, and let u0 go to infinity. Okay, so u0 is going to infinity. That means this region will become a delta function. So for this limit, when you maintain the area constant but make u0 infinite, here this will be replaced by delta function. Similarly, you will have another delta function here, somewhere here. So you are replacing this rectangular potential, periodic potential distribution by a train of delta functions. So for this case, ucx reduces to a train of delta potentials. Okay. So find out, if you use this approximation, what is the simplification that results for this particular equation. It will turn out to be much simpler and easier to interpret. Now let us point out what happens if instead of an infinite atomic chain, you have a finite atomic chain. So you have a periodic crystal potential, but you have a finite number of periods in the potential, as against the infinite number of periods for which we have just now derived the Ek relation and energy band picture. So what differences will arise if the atomic chain is made finite? For infinite atomic chain, in the allowed band, the energy E varies continuously and periodically with k. This is what you can see. So this is the allowed band of energy, this is another allowed band of energy, this is another allowed band, and in the allowed bands the E varies continuously and periodically with k. Now what will happen if you have a finite atomic chain? In this case, in the allowed band, the energy E varies in discrete steps, and the number of discrete steps is equal to the number of atoms in the chain. So here is an example shown for this band. Now similar discretization will happen for each of the other bands which has not been shown in this figure. So you can see here that this allowed band, there are 5 discrete energy levels, 1, 2, 3, 4 and 5. Why? Because there are 5 atoms here, 1, 2, 3, 4, 5. So 5 atoms in the chain, and therefore this allowed band gets discretized into 5 energies. Now let us come to some aspects of the representation of the Ek diagram. Because the Ek diagram is periodic, it is not necessary to show many periods of the diagram, because the information is contained in one period, and in fact because the Ek relation is even, you can even take 1/2 of the period, okay, and that will give you all the information that is required to construct the entire periodic Ek diagram. So let us look at this. Now the way we have shown the Ek diagram so far, it is called the periodic zone representation. Okay, let us look at this various features once again. So here the periodicity is equal to 2 pi by a. So you have marked here 0, pi by a, 2 pi by a and so on. Now this is the kind of Ek variation which results from the chronic penny model, which assumes a rectangular potential distribution, periodic rectangular potential distribution. Now something that I had not mentioned earlier, what is this curve here? Now this curve is a parabola that you would get for a free electron, right? So for free electron the Ek relation is a parabola. So that is what is shown here, superposed, just for you to be able to compare the picture for a free electron and the picture for electron in a periodic potential. Now the reduced zone representation represents the Ek behavior in just one period, okay, 0 to pi by a and 0 to minus pi by a. This is called the first Brillouin zone. Okay? This is called a Brillouin zone because this EK diagram, the way we have determined it, the procedure that we have just outlined, the chronic Penny model, happens to be the procedure suggested by Brillouin, where you derive the forbidden bands starting from the continuous energy band for free electrons. Now let us consider the EK picture for a real crystal. This was an ideal picture. The chronic Penny model is the ideal picture where you are assuming the potential, crystal potential, to be periodic and rectangular of this shape. Actual crystal potential is much more complex. Now people have done calculations, okay, for various real crystals. Let us look at the calculations for silicon. How do they look like? Now this is the EK diagram that you will come across in books shown for silicon. First let us explain the various aspects of this diagram. Now this 1 0 0 within brackets, this actually shows a certain orientation of the crystal. You know, silicon is a 3-dimensional crystal, so there can be many directions which you can consider, and you can consider the EK diagram in various directions, right? It is not a one-dimensional situation like what we have analyzed so far. So for example, say this is the crystal. Now you can move in this direction, or you could move in the diagonal direction. So let us say from something like this, right? And you will get some EK diagram because you will get some periodicity of the potential, and you will get a different periodicity if you are moving in this direction, right? Now this is the direction that is called 1 0 0. It is perpendicular to the faces of the unit cube of silicon. Now we will not discuss the orientation further. This is just to help you understand that the EK diagram is different in different orientations. So you can show the EK diagram for k vector in this direction. You can show EK diagram for k vector, let us say, in this direction. This direction would be called 1 1 1. Okay? Why this is called 1 1 1 and why this is called 1 0 0? It is beyond this course. Okay? This you can, if you are more interested in this, you can read up the books. So now for this 1 0 0 direction, from 0 to pi by a by 2. Now why is it a by 2 here? Well, as we have said, since the EK diagram is even, instead of showing from minus pi by a to plus pi by a in the entire first Brillouin zone, you can show even for half of this zone, that is from 0 to pi by a, because this part and this part, they are symmetric. So that is what is done here. The diagram is shown only for this half of the Brillouin zone. Now the reason here you are using a by 2 instead of a is that this is a one-dimensional crystal, okay, whereas here the results are shown for a 3-dimensional crystal where a is the lattice constant. It turns out that when you are moving in 1 0 0 direction, that is the direction shown here, the periodicity is related to the location of the various planes, atomic planes, and to successive atomic planes the distance is a by 2. This is a, and the successive 1 0 0 atomic planes, it is a by 2. So that is why the a by 2 is coming here. So as against this kind of variation of EK relation, here the EK relation in silicon is something like this. This is for the conduction band. In the valence band, this variation looks similar to this variation, right? So this is the conduction band and this is the valence band, that is what is shown here. These are lower bands. So you have, as you know, you have many allowed bands. So normally we are interested in the outermost band, which is the conduction band, because the electrons which have those energies, they contribute to the properties of the semiconductor, they participate in conduction and so on. Now here there are two lines, so there are two overlapping Ek relations. Now this is a complexity that arises because of the nature of the crystal potential, which is much more complex than what we have considered here. We will not discuss this point further. Now normally what one does is one uses the left hand side to also provide information of the Ek diagram if you were to move in the 111 direction. Now please note, the way it is shown here does not mean that 100 direction is exact opposite of 11 direction, right? That is not what is meant here. So I have said this diagonal is the 111 direction, right, and perpendicular to the face is 100. So those are the directions. So the diagrams in those directions. Now here instead of a by 2 you have 2a by 3, because in the 111 direction the successive atomic planes, the distance between them is 2a by 3. You just accept this result without going into why it is 2a by 3. Now that you will study if you study the crystal structure of silicon in detail. So you can see when you move in 111 direction the conduction band Ek relation is somewhat different, okay, both for conduction and valence bands. The so called energy gap is actually the distance between the bottom of this Ek relation for conduction band and the top of Ek relation for valence band. So you see that this vertical distance between these 2 points in the 100 direction is different from the vertical distance between the points in 111 direction. Here the gap is more, okay, here the gap is less, the vertical distance between these 2 points is less. Now compare the Ek diagram of silicon with that of gallium arsenide, where your crystal potential is different, right. So if you do a numerical calculation for the crystal potential associated with gallium arsenide, the band diagram which results looks something like this. The key difference between the Ek diagram of gallium arsenide and Ek diagram of silicon is that the bottom of the Ek variation in the conduction band is shifted away from the Ek variation top of the Ek variation of the valence band here. So there is a difference in k locations of this minimum and this maximum, whereas the minimum of the Ek relation of the conduction band in gallium arsenide is right above the maximum of the Ek relation of the valence band. Now this difference in the Ek diagrams is the reason why the gallium arsenide is called a direct band gap semiconductor and silicon is called the indirect band gap semiconductor, okay. So more about this later. The reason it is called direct is a vertical transition can be made from an electron can make a vertical transition down from conduction to valence band without changing its momentum, right. Now unfortunately this result is all right for free electrons but not electrons in crystal, and you have to resort to the Ek diagram to actually get these relations, okay, and they will not be exactly identical to what we have discussed. Now this is the point that we will start with in the next class. Since we have come to the end of the lecture, let us make a summary of the important points. So in this lecture we have discussed determination of the Ek diagram in a quantitative fashion in detail. This determination was discussed for a periodic crystal potential. We assumed an idealized crystal potential which has a rectangular periodic shape, and then we showed how you can solve the Schrodinger's equation for this potential and derive 3 important features of the Ek diagram of electrons in a crystal. These 3 features are: one is that the Ek relation is periodic with periodicity equal to 2 pi by distance between the atoms. So, we have assumed an idealized one dimensional situation. The next feature is that for certain energies the Schrodinger's equation does not have a solution, and therefore these energies are not allowed for the electrons. And the third important feature is that the energy as a function of the momentum or the wave vector k is a multi-valued function, that is, for any given value of k there are multiple values of E. As against this, for example, for a free electron, for any given value of k there is only one value of E. Even for an electron in a rectangular potential well, for any given value of k there is only one value of E. Okay? So, the differences between the Ek relations of free electron, the electron in a rectangular potential well and the electron in a periodic potential were clearly brought out by discussing how the Schrodinger's equation is solved. Now, we have outlined the various steps of the solution for what is called a chronic Penny model, okay, idealized periodic rectangular potential distribution. Now, the features from here can also be the qualitative features of this solution can be applied even to real crystals. So, we have discussed also the shape of the Ek relation for real crystals such as silicon and gallium arsenide. Now, we want to make a point that while the various steps of the Schrodinger's solution to the Schrodinger's equation for periodic crystal potential were outlined, we have not really gone through the various steps in detail, because such a derivation can go on to 2 or 3 classes and one can always read it up because it is available in various books. So, we have focused ourselves on the outline of the key steps in the procedure. In the next class we are going to see the utility of the Ek relation, how it can be used to find out the effective mass, the velocity and crystal momentum of the electron in a crystal, and we will also begin a discussion of how one can calculate the Ex diagram of devices.